All right, before we begin, I would like to quickly clarify something. When Mark from Civo invited us to come do this presentation here, he said, guys, one thing, you can't do a product pitch at this event. And as you're about to see, me and Dan, we're pretty passionate about this topic that we're about to present. So you could easily think that what we're doing here is a pitch. So I just want to clarify, that's not true. Right? So if you're talking to other people afterwards, you say, what do you think about this distributive thing? You could say, well, oh, wow, man, that was mind-blowing, you know? I'm going to stop what I'm doing, I'm going to do this distributive thing. Or you could say, I don't know, it sounds complicated, you know. I'm just going to keep doing what I'm doing, cloud native. I'm going to launch VMs on Amazon like I was always doing. Maybe if I keep doing that, they'll give me a fair price eventually, right? So I'm not trying to put words in your mouth here, but whatever you pick, this is not a pitch, because all we offer is the truth. In 1947, scientists from AT&T Bell Labs invented the transistor. The transistor is a very small electronic circuit. It's a small current that controls a larger current. And scientists figured out that if we interpret the low value as a 0 and the high value as a 1, we have a digital circuit that you can combine with other circuits to make OR gates and AND gates, and eventually they came up with these things we call chips or CPUs. Fast forward to 2030, Intel now thinks that they can pack 1 trillion of these transistors into one chip. Just one chip, and that's just one CPU. Now, if you look in your pockets, probably you have a mobile device, a smartphone. Could be Nokia, or could be an Apple, for example. And so and we have millions of devices. So millions of devices times trillions of transistors. That is a lot of compute, existing compute. And even if Intel doesn't make this trillion transistors in their chips, if we just stay with the chips we have today, we have an extremely large amount of compute infrastructure at our fingertips. And that's where Dan came in and says, why don't we just use that? And so we'd like to present distributive computing. And as you will see at the bottom, there's a number of different partners that will become clear as we present this demonstration.
Thank you, Jeroen. My name's Dan. I'm from Distributive. Jeroen's from Nokia. I met him at a presentation, Nokia Partner Summit, and we unveiled a new type of computing which promises to reduce the cost of compute. The example in the talk we just heard, where they're doing LLMs and everything else, is that 6 cores on AWS, etc. Well, we do exactly that same stuff, but at 10x less the cost, using compute infrastructure already in the hospital or the airport or your enterprise, or government building, or what have you. So this is what we mean by compute differently. My background's in physics. And I use a lot of computing power to make tomorrow happen today. Electromagnetic propulsion and those types of technologies, it all takes compute. So I'd like everyone to get your phones out, and we're going to demonstrate distributive computing right here, right now, to do some secure physics computations. Okay, so I'm going right to the point here. Let's look at some code. I'm going to walk everyone through what it looks like to use the Compute API, the Distributive Compute API. 2 classes, Compute and Wallet. Compute is to distribute, and Wallet is to pay in compute credits or earn them. You only need about 5 ingredients. High school students can write code like this. An array of arbitrary inputs. This could be inputs to your LLMs or CSV files, or in this case, just integers. That's the input set. A work function, which is arbitrary code, which transforms those elements. In this case, this is my physics. There's about 600 lines of code of math, and I'm not going to bore you with it, so I just hid it behind this package, and it returns the result of the computations. And then finally, compute.for. Compute.for is a parallel automated for loop that unrolls your functions automatically across devices everywhere, nodes, and brings back the results. There's no image creation. There's no Kubernetes. There's no infrastructure control plane. There's no data control plane. There's nothing. It's compute.for, results equals job.exec, and away the code goes, and you get your results back. So I'm gonna run this right now, and we're gonna use the phones in the audience to compute this. Straight up old terminal. It's asking me for my password. Jobs deployed. Now I need everyone to open on their phones or their laptops or their devices dcp.work, dcp.work/demo. And the join secret is DCP. dcp.work/demo, join secret is DCP, and click start. And you can see results are appearing on the screen as we speak. So we just created a cloud with all the devices in the audience doing secure compute. We don't care whether it's Android or iPhone or anything else. Any operating system, any chip, CPU, GPU, run arbitrary compute anywhere. And so how's that for a quick, instantaneous compute cloud? Yes? The join secret was DCP lowercase, but the job will probably be finished by the time you join.
Next time.
Next time. Or do it at home. And what's interesting about this is that you probably see that you're accumulating compute credits or something along those lines on your phones right now. You're probably wondering what those are. Well, you're making money right now. Actually, you're making me money because the payment address is mine, but you'd have to input your own, right? And so what that looks like, I'm just going to go to the bank here. Cloud. Now you're looking at the bank. You don't care about this. I only have one checking account here. Maybe I can zoom in, but you can see that I'm pretty poor. I have a couple of compute credits, but I can accumulate more by doing work for this network, either the public group or in private enterprise groups, or I can buy them. But if I accumulate them, I can also sell them. So it's a distributed computing system with a bank overlay. Right, we're measuring CPU seconds, GPU seconds, bytes in, bytes out, and we're turning it into dollars at the end of the day. And the vision behind that is, now I have to go back to the right slide here. The vision behind that is the current cloud economics are pretty simple. You pay, and they take all your money, and they're happy to do so. The entire AI revolution is basically penultimately feeding 3 or 4 companies, right? And I think 80% of VC funding is going straight to the big 4, right? So all the AI companies, they're essentially flow through money going to the cloud. What we're presenting is to rethink ubiquitous computing and digital economies. If we can measure workload and the value of that workload being done, then you can split it up and you can share it with all the people who are bringing stuff to the table. So you all passively provided compute. You get paid, but other people are providing value by providing applications, by providing network, like Nokia. Think about a big telco. In Canada, we have one named Bell, and they're a partner in this project, this pilot. They have 30 million processors in the form of gateways across the country. 30 million processors doing nothing 97% of the time. That's 106 times Canada's national research computing capacity. Idle, doing nothing. Imagine tapping into that and shifting the computing power of a nation to do more advanced research, AI, data processing, etc. And it's not us or the cloud. The cloud fits perfectly well in there. They do what they do best, which is providing access to silicon chips. We're talking about reshaping who's getting money, which should be everyone when they bring goods to the table. And the sustainability case for the ROI. Some people always ask, well, have to be making more money than the cost of electricity when I'm running my computer. Well, you better bet that if the value of the compute was less than the cost of electricity, cloud wouldn't exist either, obviously. Okay, right? So in Ontario, it's about 10 times more ROI in terms of the cost of electricity to the value of compute in our model, which makes it 10 times cheaper than cloud for the get-go. So everybody wins in this scenario. This is why it's important. So now I want to motivate why that's important. GDP goes up as a function of compute capacity in a country. Of course, you produce new medicines, you structure new aircraft, you design new things, you put out all this foundational model stuff that everyone's talking about. Compute is the gateway to innovation, period. I'd like to point out that Canada's not really doing too well. We're at the bottom of the G7, and we're trying to fix that. And so this came out literally 2 weeks ago. Canada and the UK are signing these joint memorandums to share computing capacity, to make it affordable, and to make it not as damaging on our environment. This is a true snapshot with some numbers of what's going on in Canada specifically, and Canada's a G7 country, right? So if we're doing this badly, think about most of the rest of the world needing to get access to compute if they want to participate in these digital economies. Because otherwise, this is what's going on. Surging demand is driving huge costs for compute, and it's putting a damper on innovation. And to keep up with this demand for compute, we're building data centers literally in your backyard. And by we, I don't mean distributive, I mean the big four. And to compete, you must compute. So the demonstration that we just did using your phones in the audience, that was just the really quick, in-browser demo. Now we're going to show you the same thing, but instead of a simple physics demo, it's going to be a gigantic astrophysics research computing application that's going to go out to about 1,000 cores spread out internationally across all these partners using literally exactly the same code. This application, not that we shouldn't really care about the use case because compute is compute is compute, but the science here is interesting, so I want to share it with you. If you measure the tangential velocity of stars around the center of a galaxy, you can infer the presence of dark matter. And what we found when measuring the rotational curves of these galaxies, the speed of these stars is way faster than what they should be according to general relativity, almost as if they're being held in by more mass than what we actually see. And this is what gave rise to this notion of missing invisible mass. And that's dark matter. And so it's important to be able to characterize these velocities and to put the error bars on the measurements. And that's precisely what an application called DiskFit, which is a small subset of applications that's going to be deployed within a $2 billion radio astronomy international project called the Square Kilometer Array Observatory coming online in the next few years. We're getting a head start on some of the applications with the researchers in this project to unlock vast compute affordably and sustainably. So in this application we're about to demonstrate, normally one fit is done locally, and then you'll do up to 2,000 in a distributed fashion. And what's cool here is that, again, just like the code I showed at the start of this presentation, this is how you would write a normal for loop. I'm sure everyone here has written a for loop. Rewrite that like this with the compute.for syntax, and it will take the bootstrap function, map it to the all 2,000 inputs, results equals job.execute, finished. So let's send this right now to the world.
Live demo.
Live demo. So this is the same code, but for this different application. And notice it's the same thing. Input set, range. The work function is that complicated bootstrap stuff. And behind bootstrap, there's, again, any amount of code that you want to write. Compute.for is the job. And here, before we had one compute group called demo for the audience, we just added a whole list of other compute groups. So those are all the partners. And when we deploy this, it's the same thing. We're going to send out 2,000 of these. And for reference, this job normally takes about a week to run locally or more. Jobs being serialized, and that's going to deploy, and it's going to go worldwide. It'll probably take about 40 minutes, which is more than what we need, or more time than we have available, but we'll start to see results trickling back, and I'll let that run in the background while we talk a little bit about these partners. But what I wanted to highlight was that was trivial. High school students can write huge, massively parallel code and send it to infrastructure all over the world, and everyone gets paid. So back over to the presentation, and I'll come back to see those results as they're trickling in. One of the groups, HITA, they're based in the UK. They've attached servers to water tanks in residential homes. All of the heat from those astrophysics computations that are going on right now is being recycled into hot water tanks, saving the average household about 400 pounds per year worth in energy heating bills. This is sustainable computing. Carnot, mainly similar idea in France. They're doing the same thing, but more at the residential level, where they're taking the heat of compute and dumping it into the hot water pipes that flow through buildings.
District heating of Paris. Sorry. They do the district heating of Paris, for example.
Deep Green, based in the UK, they reject the waste heat into residential swimming pools, so that people can swim and I guess sit in hot tubs.
Yes. So the problem in the UK is, of course, the energy prices there are rising, and so lots of pools have had to close down because they couldn't afford it. And so Deep Green came in and said, if you host our compute servers next to your pool, we'll pay the power and we'll give you the heat, and then so the pools can stay open. And so what we're trying to do is we think that the government of the UK should be able to invest in Deep Green, and whereas today they invest in AWS, right? Because Deep Green is too small to be able to service to act as a partner for the UK government. So if we can bundle the compute and aggregate the partners, HITA, Deep Green, and lots of others, they can be a compute cluster that the UK government can buy from and invest in.
Cloudbear, based in the Netherlands, they provide a whole suite of DevOps services so that developers can focus on developing and not on DevOps, but they also have data centers. And they have an interesting model where they take advantage of advantageous electricity pricing locally. So they too are providing compute in this large aggregate model. Rooted Labs, they are decentralized microfarms using containers retrofitted to grow lettuce heads and vegetables, and they're heavily into IoT to measure data and augment the growth of their products using compute. And so all those computers across all those containers can also form clusters to, when idle, power technical agri-tech companies, right, instead of the cloud. So it becomes this circular economy where money by other startups or companies can be reinvested into these compute economies and literally grow lettuce and grow food, heat swimming pools, heat hot water. World Community Grid is in this group. They alone are providing about 500 cores in the demo we're doing that's running in the background. They have 800,000 volunteers, about 2.4 million chips doing scientific computing right now. We've augmented that. Those of you who are familiar with SETI at Home, this is the group that ran SETI at Home, or the same technology, except it took a long time to bring jobs up and onto their network. It would take from a month to a year. With the API, the distributive computing APIs and technologies, it takes an afternoon. So I think we're coming close on 25 minutes. Call to action. We want to rethink and reshape digital economies. Okay, instead of feeding the four main cloud providers, let's bring that money back and redistribute it to everyone who's providing a piece of value in these technology economies. Make it accessible to everyone. It's free for universities and schools everywhere, and we're open for commercial partnerships. Thank you very much, Civo, for inviting us to talk, and to all of the partners who showcased compute on their infrastructure simultaneously. Are there any questions?
How you doing? I'm Emmanuel from New York, Hofstra University. A similar initiative to what you showed us with the deep green we have in New York City. We have a very well-funded saunas, and one particular company uses heat generated from computing, crypto computing. So you talk about going local and being in major cities. So New York City's benefited from these initiatives as well. So I'm happy that you brought that to our attention. Thank you.
Thank you. And
We would like to have references like that. Like if you know other companies that are doing something similar to these companies, please let us know, because we think we can participate.
yeah, if you know other companies, we'll join in. Like at the end of the day, this is a mechanism to flow funding to sources of compute, right? Bitcoin mining is not that profitable. Otherwise, it would be running on AWS. It's not, because it's not valuable compared to looking for tumors in MRI images, or training these models, or active inference, et cetera, et cetera. So I bet you that if we plugged into your system, it would be 3-4 times more valuable than Bitcoin mining.
Thank you. I am from Bell, Canada. So yeah, nice to meet you guys. Even if we are very, very interested in the technology, I want to be perfectly honest. We are not yet official partner. So just want to be very, very accurate on this. And that was my comment. So, thank you, Dan.
Merci.
What prevents a big player from providing a huge amount of compute power and monopolizing the system?
If a huge player provides a lot of computing power, then we have a very powerful compute network, which makes it very attractive to demand. We use a bid-ask system on the public network, where you can either pay market value, which causes your workload to go out at a normal priority, or you can go above or below. If you flood with supply, then the supply will be idle if there's not enough demand, and vice versa. Except if we have too much demand, then we burst onto World Community Grid and other large supplies that can absorb it. So that's not a problem.
Hey guys, how do these vendors accept your connection? Do they already have these auto accept type things on their compute system? And then also, how reasonable is it to think that a company could actually use their employees' computers on off hours to do this and not use the cloud during times where employees maybe not even using their computers?
So in terms of the packaging and deployment, we have a slide for that. So we sort of skipped and went all over the place here. We've shown this running on fridges and watches and just about everything else. So Tesla cars, what have you. In terms of the packaging, the workers can run on anything from within browser tabs, which is the demo we did in the audience. Also Docker workers or screensavers for schools or whatnot. It doesn't matter. We can basically, if you have an environment, the DCP worker will work in it. They make outbound connections to a scheduler, so there's no firewall exceptions or poking holes or anything like that. It's all HTTPS. So from a sysadmin's perspective at an enterprise, it looks like people surfing Chrome. Is what this looks like. So those same securities. In fact, it's built on the same technologies as Chrome. So in the background, it's V8 and WebGPU doing the compute. So it has the same security guarantees that Google makes when talking about executing random JavaScript on people's computers. But I'm just going to answer part two. And then the second answer was, how reasonable is it for people to expect their employees to use this on their own computers? That's the company's own prerogative to create various opt-in models and incentives. So a company might have their own company-owned infrastructure they can deploy these clusters to, and if they want to boost it with other infrastructure that's not theirs, then they have to talk with them about what those incentives look like, or opt-in mechanisms. That's not we put the technology out there, and it can be wrapped with whatever business model makes sense. Other questions?
Thanks. Hey, really cool idea. I'm curious. the data you're getting back, is it only related to computation of the code you're requesting from the distributed server group, or are you getting like other stuff back, like open tabs on the browser, etc.?
Thankfully, Google, Microsoft, Apple, and Mozilla have put billions of dollars over the last 2 decades into making the web stack secure, interoperable, anonymity, you name it. And so when you send a job, you only get your results back. You don't tap into anyone else's stuff, and you cannot, unless you have nation-state resources to do browser escape and stuff like that, it has the same reassurance and security that you have when you surf the web doing all kinds of random Google searches and then all of a sudden sign into your online bank. That's pretty wild when you think about it. You're executing untrusted code from all over the place and then you're signing into your bank. That's wild. What a great technology to build a computing platform on top of. It's literally designed for securely executing untrusted code anywhere, on any operating system, any chip, and giving you your results back.
Yeah, thanks a lot for the demo. My question was about the economics of it. So the pricing model or the incentive that you get back by providing compute, the rates and the economics of that, how is that driven? Is there one entity which controls that? Is there any scope of someone being a bad player in this space?
It's a good question. So the pricing of this compute model, I was sharing earlier, these compute credits, one compute credit is 100 CPU second reference CPU seconds, or 2.6 GPU reference GPU seconds, 62 kilobytes in or 62 kilobytes out, or a linear combination of those 4. That's the value of this thing. It costs about 200 times less than that in electricity to produce, and then it gets split up and it goes to the various entities that are doing compute, providing applications, etc. Right now, this all exists in a single ledger. That ledger eventually, if this is what you're asking, could be made auditable or put into some form of blockchain if required. It will make it less efficient to blow something like this. All the compute transactions over blockchain, it doesn't really make sense. A lot of companies have tried and failed. But it's relatively easy to open the ledger and make it auditable if that's what you're asking. Right now, there's one scheduler and one bank, and it's being run by Distributive. The vision is to take this and put it on internet exchanges and other places all over the world and have everyone manage micro compute economies in their own countries. We're done? We're done. Okay, we're done. But please come talk to us. Yeah, thank you so much. Come talk to us after this if you want to hear more.